Alright, welcome to the first of the two videos on Jupiter. This is just going to be kind of quick overviews of the giant planet. Just some beautiful pictures of Jupiter. This is from a telescope on Earth, obviously, but you can see the 4 Galilean moons here. I thought that was an interesting shot. Just kind of shows a lot of the different banding on Jupiter, which is important when it comes to the weather on the planet. Well, it's a big one. They don't call it the giant planet for nothing. It's 318 times as massive as Earth, right? So, 11.2 Earth radii from the center area. Volume-wise, though, that would hold about 1,400 Earths. It's big. So, it's big. We'll address that in class. Well, it rotates differentially. Now, this is confusing. Because terrestrial planets obviously rotate what we say uniformly. They all rotate the same rate. That's because they're rock. Well, gas rotates differentially when it's on a planet as large as Jupiter. Now, it also does this on the Sun. The Sun is actually one of the first places we noticed differential rotation of gases, and Jupiter also does it. Every gas planet rotates differentially. So the equatorial region rotates at about 9 hours and 50 minutes. The poles rotate around 9 hours 55 minutes. It's not a significant amount of time. Difference, anyway. But on the Sun, it is actually several days difference, but the Sun's a lot larger scale. So it flattens as it rotates. So the planet itself doesn't look very spherical as from a point of view of like Earth or something like that. It's kind of squashed like a balloon that's kind of roundish, and then you kind of apply pressure to the top and bottom of it, and it kind of flattens out, much like the solar system did with the nebular theory. It tries to start doing that, but it's just obviously doesn't have the angular momentum required to flatten out entirely. That's because it's not all gas. There's some kind of weirdo thing in the core region that scientists speculate to be about 5 or 10 Earth masses. Now, we identified as some rocky type of core. Now we're going to talk about that in the next video a little bit more. It's a question mark. It's totally a question mark as to what's in the center of Jupiter. So if Jupiter wasn't rotating, it would kind of look spherical, more spherical. What you see here is it kind of looks more like an oval. Because of the different, what do you call it, vectors being exerted on the planet as it rotates. So it's obviously the most massive in this region here, so it's exerting more force, right, as denoted by the length of the arrows. Physics connection. So the Great Red Spot is this massive storm-like thing. It's the most well-known feature of Jupiter. It's been around for at least 400 years, and we say that because it's first identified by Galileo. We are not sure if it's going to stick around or if it kind of comes and goes every few centuries, which, you know, again, astronomically is a small amount of time. Looks like a hurricane. It's not the same as a hurricane because hurricanes form over water and have a lot to do with combination of the rotation of the Earth and the increasing temperature of the water around the equatorial region. That's not really why the Great Red Spot is there, we do not believe. It is not related to water. at least as far as we can tell currently. It just happens to spin like one. It looks structured like one. It's huge. It's about 2 times the size of the planet Earth. So if you look back at this picture, right, Earth would fit within about a size about like that. It's really, really, really large. I said it's 400 years, been at least 300 years. Sorry about that. Galileo saw it in the late 1600s, so it's approaching 350 years, something like that. But anyway, it could be going for millions of years. It could continue to go for millions of more years. The planet itself is very star-like, at least in composition. It's about 86% hydrogen, about 13% helium. Other gases make up the other 1%. There's water vapor and some other things, right? And obviously every other gas. And there's also every element on the periodic table on it. It's one of these things when we say it's a gas planet, it's not all gas. It's mostly gas. At least the volume part of it. Now stars are more hydrogen and less helium, especially when they're younger. But it's well on its way to being a star. If it had about 80 more of those, if it had about 80 Jupiters combined, it would form a star. Now it's got these different colors here, and the reason it has different colors is it has what we call atmospheric bands. And the atmospheric bands are basically giant convection cells within the planet. And the lighter colored bands are where warm air is rising, and it's been able to basically push out and decrease the density, and therefore it decreases the color because it's less thick. And then when it cools back down and contracts again, it gets darker. As you can see it from here. And as a result of that, as it starts to sink down, it forms this darker colored band. And the bands go in opposite directions. So in this case, the darker, cooler material that's sinking is going in this direction, and then the warmer material, as it's convecting up, is going in an overall direction of this. And I'll show a video in class that really shows those bands moving. It's really, really cool. It's one of those things most people didn't realize they actually moved. So we call them zones and belts. No, I didn't mention that. So you have a zone is the lighter regions, right? Like this is a zone, and then this is a zone, and this is a belt. So belts are the darker ones. It says different bands travel high velocities, so they're much like jet streams on the Earth. Some of them, especially around the equatorial regions, travel quite rapidly. So in this sense, you have to look at the velocity. This is a confusing graph. You're not really paying attention. This zone here is not going negative 250. They're just saying it's if this is prograde, right? This is the positive end. And this is 0, this one's going this way, so it's going what they're classifying as negative. So make sure you understand that it's really not going negative kilometers per hour. This one just happens to be pushing this way, right? And this one's pushing this way, right? So this is pushing this way, and so forth. But it's just interesting because they're going back and forth because there's zones and belts, zones and belts, zones and belts, zones and belts, zones and belts. So. Now, we kind of classified the different atmospheric layers based off of some data we got from the Galileo probe that was sent into Jupiter to test this atmosphere. So, the real question is like, what is this, altitude is a question mark, right? And it's basically expressed in pressure of Earth atmospheres. So, this would be what we would think of as sea level. So, Okay, as I was saying before I got cut off by the afternoon announcements, we kind of say this is roughly the one atmospheric pressure on the planet Earth. So as Galileo is descending into the planet, he's taking all these different atmospheric readings, pressure readings as well. So we identified some layers as we would think of them in the stratosphere here. I'm not sure what the haze layer is. You have the troposphere. The troposphere is the weather zone. And in the weather zone, we see ammonia ice clouds. Below what we consider one Earth atmosphere, you start to see some different funky stuff going on, including water ice clouds down here. And then, as you keep descending further and further in the planet, you should also notice that the temperature keeps increasing more and more, which that's not a surprise. But down here is where it kind of got funky and the Galileo really lost the data. Sorry, got interrupted again. So down here you have what we're considering, or what we're calling gaseous hydrogen and helium, and then some other trace stuff like methane, ammonia, and water. So this is like really where the gas of the planet is, right? Not to say that this isn't, but this is where the major constituents are. Constituents? I don't know. Components? Probably. I don't know. I don't teach English. So, different atmospheric compositions and the fact that it is, hotter in certain places and colder in certain places of the planet will cause gases to convect. And these convection cells we've already seen will form things called zones and belts. They also tend to form these storms that kind of come and go. And there are three different major classifications of storms. So the red ovals, like the Great Red Spot, are the largest, and we've only seen a couple of other ones that are like the Great Red Spot, but they dissipated. White ovals are kind of a medium-sized oval storm, and they're shorter lived than the red ovals. They still last for several years. The brown ovals are really kind of a smaller storm, and when I say small, you really got to think this still about the size of the Earth, but they are short-lived. So this shows some different spots here. There's a white spot. That's another red spot. So, and these kind of get trapped in between zones and belts, and the gas kind of rolls over. Like here, you can see that one gas is going this way, and another gas is going this way. It may not be easy to see that, but I'll show a video in class that does show that. That's a shorter or smaller brown oval, right? Those are a little more short-lived. Now, if you remember back to that picture as well that I had of the Great Red Spot, that's a great image of a white oval right there that was short-lived. Still large. Remember, Earth would be about here, right? Still large, but they're a little more short-lived. That's a little tiny one right there. So, anyway, sorry about all the interruptions. What can I say? It was Grady High School. So, and we'll pick up with the internal structure of Jupiter in the next video.